Hey guys, welcome to the mini lecture on the emission spectra and the Bohr model. In this lecture, we're going to continue laying the foundation for understanding quantum theory by extending our discussion to a topic that's extremely relevant to the field of chemistry and of course beyond chemistry, which is this topic of atomic emission and absorption. In previous lectures, we talked about quantum mechanical effects in the context of the double slit experiment and the photoelectric effect. In this lecture, we're going to present yet another aspect of quantum mechanical behavior that is essentially unable to be described by classical physics. And this will actually be our last topic that we present in our motivation of quantum theory before we start going into building up quantum theory proper for atoms and eventually molecules. So first up, let's talk about emission spectra. So the definition of emission spectra is simply the spectrum of frequencies, wavelengths, different types of light that are emitted by a given element or chemical compound. And this emission process occurs by essentially having a high energy state, and this could of course be a high energy atom or a high energy molecule, and having that high energy atom or molecule transition to a low energy state. And of course, if we're losing energy in that atom or molecule, that energy must go somewhere, and oftentimes we'll find that that energy is released as a photon. So we end up with a low energy state in that atom or molecule and a photon. Okay? So the interesting thing about these emissions is that the different types of photons that are released only come in discrete regions of the electromagnetic spectrum. So for example, if we look at, say, an oxygen atom or a neon atom, we can look at this emission spectrum for either one of these elements, and we observe that there are very distinct bands corresponding to the wavelengths of light that are emitted during these transition processes. And now notice that the bands are different depending on what sort of element you have. So for example, oxygen has some very distinct bands here in this green region, but there's no counterpart in that neon atom. So this is extremely useful in a number of different applications. So one of the first is this use of emission spectra as a sort of molecular barcode. You can use the unique colors that are emitted by these high energy atoms and molecules to identify what atom or molecule you're actually dealing with. So one technique that's used in a laboratory setting to help identify different compounds is a so-called flame test. Okay? So a flame test uses the energy from a flame, from burning some sort of hydrocarbon, to create high energy or excited molecules or atoms, and then once those molecules are excited, we can observe that emission process of those high energy states going back down to low energy states and the subsequent emission of a photon. We observe that photon and we see these nice different pretty colors illustrated here for the four different representative elements. So this presented a number of problems. So if you're looking at that classical model of the atom where you have protons, neutrons in the middle, and these little electrons flying around the outside, okay, it's impossible for us to rely solely on that classical physics model of a nucleon with the electron flying around and account for the fact that only discrete lines show up on these emission spectra. So a number of scientists started to come up with different ideas to help describe and ultimately be able to predict these different wavelengths of emission. One of the first equations that was first put forward to describe this emission process is the so-called Rydberg equation. And it was described to predict the wavelength, lambda, of any line segment, any line in the emission spectrum of hydrogen, illustrated right down here. So the key elements of this equation, first off, I want you to note that the wavelength here on the left-hand side of the equation is given as 1 over that wavelength. It's often a point of confusion for students when they're working with this equation. If you're trying to solve for wavelength, you're going to have to do a little bit of rearranging here at the very end. Okay, so 1 over the wavelength is equal to r, which is yet another constant given to us here, multiplied by the difference between two different states in which that molecule is found. So this is something that, we didn't, at the time when this equation was put forward, we didn't have a very good understanding as to why, but it was noticed that if you assign certain integer values to these n1s and n2s, we can talk about transition processes going from different values of n. These n's are integer values, and they're specific integers such that they are both positive and n2 is greater than n1. So if n2 is greater than n1, then that means that this term in parentheses here is always going to be positive. The Rydberg constant is a positive, and we're guaranteed to get a positive 1 over lambda, and hence a positive wavelength. So in order for this equation to make sense, we have to have those constraints on the integers. But beyond that, what we basically are seeing here is that if you set up certain discrete values of n and look at differences between these different n's, and we're taking them squared, we can account in a very succinct mathematical way for each one of these lines in this hydrogen emission spectrum. Now again, we don't at this point know why this occurs, but this equation at least provides a quantitative prediction for where these lines are going to be showing up on an emission spectrum. So one of the founding fathers of quantum theory, Bohr, actually spent a fair amount of time exploring these emission spectrum, trying to come up with a sort of theoretical foundation as to what's essentially going on here. And so the Bohr model puts forward a set of postulates, 3 postulates that we want to study in detail here. And again, the goal of these postulates is to basically describe, to be able to understand these emission processes. So the first postulate is that hydrogen atoms in general have only certain allowed energy levels. Okay? And we're going to call these energy levels stationary states. And each one of these stationary states is associated with a fixed circular orbit. And the higher the energy level, the farther the orbit is from the nucleus. So we can think about this as like a nucleus right here. We can have one orbit here, one orbit here, right? And this orbit on the outside is going to be the higher energy orbit. And Bohr postulated then that as long as an atom is in one of these stationary orbits, it does not radiate energy. Now, this is in direct violation to classical physics. If you have a charged electron around a charged nucleus moving around, we would predict energy constantly being given off. But Bohr is saying that simply can't be allowed. We're going to set a postulate out there saying that as long as you're in one of these fixed allowed orbits, then energy is not being released. However, if you move from one of these orbits, say from this orbit, the lower orbit, to the higher orbit, or back down, right? Any transition between those two orbits, then you will essentially emit or absorb a photon. So in other words, if you're at one of these lower energy orbits, so our nucleus is down here, and you want to move to one of these higher energy orbits, so we could say we got a little electron right here, what you're going to need to do is absorb a photon. Once that photon's absorbed, then that little electron is now going to be in that higher energy orbit, and the energy of that photon, denoted here by h nu, has got to be exactly equal to the delta E energy difference between these two stationary states. And so Bohr went through and assigned a specific quantum number, right, n, which, as I said before, is going to be some positive integer. and that each one of those quantum numbers n is associated with a certain radius of an electron orbit. So here's a little bit prettier illustration of what we had on the previous slide. So we have a lowest energy orbit, n equals 1, larger energy orbit, a little bit further away from the nucleus, n equals 2, and an even larger one, n equals 3. And it turns out that with these postulates, we can look at our experimental observations and come up with a little mathematical model to describe the energetics of the setup. And it turns out that the energy of any one of these orbits, so the energy of, say, the nth orbit, is given by this constant value, minus 2.18 times 10 to the minus 18 joules, right, multiplied by 1 over n squared. So the higher the value of n here, right, the larger this denominator goes, and we start shrinking down this negative value. So basically, we're starting off, like the 0 point of energy is up here, and we're starting off at some very low energy. And it turns out that if you plug in the lowest value that n can take, n starts out at its lowest at 1, and then goes all the way up to infinity. And as that n goes up to infinity, we're going to be approaching a 0 energy, because 1 over infinity is, of course, 0. And for each one of those steps in between, we go to higher and higher n. The steps, each one of the steps in the ladder, they're getting closer and closer together and approaching that 0 point. And so, of course, that 0 point, as n gets really big, that corresponds to basically removing that electron from the nucleus. Okay, so that's the basics of the Bohr model, and we'll look at it in more detail, quantitatively here in a minute. But before we do that, I want to introduce some terminology that's going to be useful not only for the Bohr model, but for our further chemical discussions later on in the course and in your future studies. So the first term that I want to introduce is this concept of a ground state. So the ground state refers to the smallest stationary state, or the smallest orbit. As I said before, that corresponds to an n equals 1. So basically, you can't go any smaller than an n equals 1. So here's one of our first attempts to explain why an electron doesn't spiral into the nucleus. Well, it doesn't because it can't go any further than that n equals 1 orbit, that stationary orbit, period. Okay? Again, that's not real satisfying, and we're going to have to essentially develop more theory to get a better appreciation for this. And that will come in the next lecture when we introduce quantum theory. But for right now, we're limited to this Bohr model where we have these circular orbits illustrated here, and the smallest one is n equals 1. So that's the ground state. If you have a hydrogen atom, then you're going to have an electron right here if that hydrogen atom's in the ground state. If you place an electron in any one of the higher energy orbits for any n greater than or equal to 2, then we call that configuration a so-called excited state. So ground state is the lowest possible energy, n equals 1. Anything above that is an excited state. So of course, n, as I said before, goes from 1 all the way up to infinity. So there are an infinite number of excited states, right? Anything 2 and above. So the processes that Bohr postulated must occur in order for transitions between these two states to occur is this absorption or emission of a photon. Okay? So absorption basically means a photon's coming in. That photon's coming in, and it's going to interact with that atom. It's going to move that electron from a lower energy state. Here it was n equals 1. Right? Photon comes in, and then it can jump that electron out to another stationary state. In this case, we'll jump it all the way out to n equals 3. Okay? So the atom absorbed energy. It absorbed a photon, so we call it an absorption process. Okay? Now, let's say we're out here at an n equals 3, and that electron moves down here to this n equals 2 state, as we've illustrated on the picture. Then this decrease in energy from n equals 3 to n equals 2 corresponds to the release or the emission of a photon. So put it diagrammatically by following the energy diagram here using the equation on the previous slide. We're starting off as n equals 3 going down to n equals 2. The y-axis here is showing energy. There's going to be an energy difference here, and this delta E energy difference corresponds to the energy of the emitted photon. So let's examine that process from a quantitative perspective. Okay, so Bohr's model gives us the energy of any given state, and we can then use that to determine the change in energy, delta E, corresponding to a transition between any two different states. So for the sake of simplicity, we'll just call the final state, wherever that electron ends up, E final, and the initial state, wherever that electron started out, E initial. So this delta E, final minus initial, is going to be given by equation number 1 on the previous slide, which tells us that the energy of the nth state is minus 2.18 times 10 to the minus 18 joules, right? And we then multiply that by 1 over n squared. So if we have a final minus initial, we're just plugging in this equation twice, and we arrive at equation number 2. So to see how we could put this into use, let's suppose we've got a hydrogen atom in the ground state. So if that electron's in the ground state, ask yourself, what does that mean about n? N must equal, pause the video there, n equals 1. Okay, must be ground state, n equals 1, and it is absorbing a photon of ultraviolet light. So through this absorption process, that electron ends up jumping all the way up to the n equals 4. So you've got an n equals 1 all the way up to n equals 4 transition, and we want to calculate the change in energy of the atom. So given n initial is 1, n final is 4, we plug everything into equation 2, our final minus initial, 4 minus 1. Don't forget to square these terms, right? We're squaring them. Okay, very common mistake that I see students make. They'll plug in the values of n, but forget to square them. So after we square them, we get our 1 over 16 minus 1, and we find the delta E, the change in energy of that atom through this absorption process. So this Bohr model and the Rydberg equation, which for the hydrogen atom gives us comparable information, gives us sort of a first glance approach at how we deal with these quantum problems that are arising. Namely, we see these discrete emission spectra, right? And so how we're accounting for that by basically somewhat artificially imposing these constraints and saying, well, the only energies that this system is allowed to take are values that correspond to certain integers n, and we can also extend the theory a little bit to account for atoms beyond hydrogen by including an nuclear charge term here. Okay. But this model only works if you have one electron atom. So we're talking, like a helium plus, lithium 2 plus type situations. And of course, that doesn't account for the vast majority of the periodic table and the vast majority of the behavior of atoms and molecules. So really, what we're left here is, just that. We've got a way that we can calculate transitions between different energy levels, and you'll get a chance to do that in the associated practice problems here in a minute. But we have a very incomplete picture. We don't know why only certain values of n must be allowed, and we don't have a theory that's more general to allow us to predict emission spectra for any element or molecule. Okay, so Bohr model, completely silent as to why this stuff even occurs, and it leaves a lot of unanswered questions, and so that's going to lead us then to basically quantum theory, right? The need for quantum theory. And in our next lecture, we're going to start diving into the fundamental developments of quantum theory as they pertain to first the hydrogen atom, and then we're going to extend our discussion to atoms in general throughout the periodic table.